Okay, let's get things started. My name is Bill Griffin, Professional Development Manager at Informs, and welcome to our latest offering in our sponsored webinar series. Today's webinar is titled Solving Bilinear Programming Problems with Gurobi Optimization. Your panelist today is Pano Santos, Senior Technical Content Manager at Gurobi Optimization, and he is joined by his colleague, Isela Warner, Director of Marketing. Pano retired from Hewlett-Packard Enterprise as Distinguished Technologist. During the 23 years at HP Labs, he developed and implemented several decision support tools for mathematical programming applications for workforce planning in the service industry, supply chain planning, CRM, transportation logistics, and operating room scheduling. Pano will deliver what I'm certain will be an informative presentation, and we will reserve the last 15 minutes for Q&A. Feel free to submit questions via the Q&A function in Zoom, and we will ask them at the end of the presentation. So thank you all again for joining us. And without further ado, I'll now turn it over to Pano. Pano, take it away.
Thank you, Bill. Hello, everybody. It's an honor and a pleasure being with you this day, morning, afternoon, and evening. You are coming from all over the world, and I thank you for that. Today, I'm going to talk about how to solve three bilinear programming problems. And these bilinear programming problems will be formulated using the fabulous Gurobi Pi, which is a Gurobi Python API that we have, and solve with the Gurobi optimizer. And in this talk, I will talk wearing my practitioner hat. I used to be a customer of Gurobi, and I would like to emphasize the power that we have in terms of modeling based on the Gurobi Python API. I used to be to use GAMS. It was nice at the time. When I joined Gurobi, I started learning a little bit of Python and the Gurobi Python API, and I tell you, this modeling language is just fabulous. I strongly recommend it because you have both the power of Gurobi itself and of Python, that is a true language that you can do a lot of things. So this is the purpose of this webinar. These three examples are going to be to show you how the formulation can be done with the Gurobi Python API, and then the power of the Gurobi optimizer. So the first problem that I would like to discuss is called the agricultural pricing problem. And this problem is an example from the very good book by H.P. Williams called Modeling, Building in Mathematical Programming. And this is example 21. And in this problem, we want to determine the prices and demand for dairy products of a country in order to maximize total revenue derived from the sales of these products. Really, this problem is a market equilibrium problem, and we are going to formulate it as a quadratic optimization problem using the Gurobi Python API, and we are going to solve it with the Gurobi optimizer. So let me describe a very simple instance of this problem. So we have a government of a country that wants to decide what prices should be charged for its dairy products, and consider four types of dairy products: milk, butter, and two kinds of cheese. And we are going to call it cheese 1 and cheese 2. And the raw material from the raw milk to produce these four products are going to be fat and dry matter. So in this table here, we have the composition. When you are producing milk, 4% of the milk will be fat and 9% will be dry matter. And for butter, 80% will be fat and 2% dry matter. So it's not good for a diet, butter, and the rest is similar, no? And the capacity or the availability of the raw materials. So we have 600,000 tons of fat and 750,000 tons of dry matter. Also, we are going to consider the last year domestic consumption demand and associated prices. So, for example, the demand of milk from last year was, and this is in 1,000 tons, was 4.82, and the price per ton was $297. And also, in this model, we are going to consider elasticities and cross elasticities of the products. So for milk, the elasticity will be 0.4, and the cross elasticity from cheese 1 to cheese 2 is 0.1, and from cheese 2 to cheese 1 is 0.4. Also, the price index cannot be raised higher than last year. So this constraint established that the new prices must be such that the total cost of last year's consumption would not be increased. And the last year price index is going to be $1,939. And the goal is to determine the prices and demand that will maximize total revenue. So let's go now and formulate this problem as a quadratic programming formulation, and we are going to use the Gurobi Python API. So the first thing that you do when you formulate the problem, you write your code using the Gurobi Python API, you will import the Gurobi Python modules and other Python libraries, and this is the code that will do that. And for this problem, we are going to have two sets, a set of what we are going to call dairy, and these are the dairy products, and another set with the components or the raw materials of the dairy products. And the parameters that we are going to have for this model is going to be the capacity, and this will be the yearly availability of component C in thousands of tons. Also, another parameter is going to be the quantity per, and this is the percentage of component C in the dairy product D. Also, we are going to have the consumption, and this is the last year domestic consumption of dairy product D. We are going to have the price, last year price of the dairy product D. Also, the elasticity for each of the dairy products, and then the cross elasticity of domestic consumption of cheese 1 and cheese 2, and cheese elasticity to 1 will be the cross elasticity from cheese 2 and cheese 1, and the price index reflecting the last year total consumption cost, which is going to be needs to be satisfied. So how do you implement the data in using Python and the Gurobi Python API? So basically, you define the set of dairy products as a list, and then you will have another list of the raw materials that we are going to call components. Then Greg Glockner, which is the one that has developed the Gurobi Python API, has created a function that is called the multi-dig function. And this multi-dig function splits a single dictionary into multiple dictionaries. And the input dictionary should map each key to a list of n values. And this function will return a list of shared keys as its first result, followed by the n individual Gurobi tuple dictionaries. So to define the parameters of this model, we are going to use these multi-digs for, as a matter of fact, for all the problems that I'm going to present. Is very powerful and very natural for us using ample or GAMS and all of that. This is the way that we enter data. So for the quantity per parameter, the keys of this dictionary are going to be the raw materials, components, and the dairy products, and this will be a tuple. So for example, the first tuple is fat and milk, and this this will mean the percentage of fat that you need in the production of meal, and this is 4% or 0.04. And the rest of the information here is for the other components and other products. So to define the capacity available of the components, we have another multi-dig function here. And the keys of this dictionary are going to be the components, the raw materials. So it's going to be fat and dry matter. And the units are in thousands of tons. So we will have 600,000 of fat and 650,000 of dry matter. Also, for other parameters related to the dairy products. So here, the dairy products are going to be the keys. So this is a tuple, but with just a single component. And this is where you see the power of the multi-dig. You have several parameters defined in the same table. No? So consumption, price, and elasticity. So for milk, the consumption is going to be 4.82. The price is going to be 0.297, and the elasticity is going to be 0.4. The other case will have similar information. The elasticity from cheese 1 to cheese 2 is 0.1, and the elasticity from cheese 2 to cheese 1 is 0.4, and the price index is 1.939. So now let's start building the model. So we are going to create a model object that will capture all the information that you need to build a mathematical programming model. So in this case, this object is going to be called a model. And this object model is going to capture the decision variables, the objective function, and the constraints. And since we are going to solve a quadratic optimization problem, we need to tell Gurobi that we are going to do that. So we have a global parameter called non-convex that we set to the value of 2, and that will tell Gurobi that we are solving this quadratic or bilinear problem. So this is the code to set the non-convex parameter equal to 2. And then to define your variables, there is a method of the model object that is called add vars. And this method returns a tuple dig. And the keys for the tuple dig are derived from the indices of the arguments. So in this particular case, the indices are going to be the dairy products that we have, that list that we created. So for each dairy product, we are going to create a variable, and all of those variables are going to be captured in this QBar object. And also, this will be the name of the variable, which is exactly the same name as the object. And there are other arguments that we can use here, but we are using the default. So as default, the variable will be non-negative continuous, and there are no upper bounds or lower bounds. And for prices, again, we use the same adverse method, define it over the dairy products. And this will be the name of the price variable, and this is the object of where all the variables are going to be captured. Now, the objective function is going to be a quadratic function where we want to determine the equilibrium of volume and price. So this is expressed as the product of the quantity demanded of each dairy product times the price of that dairy products. And this will generate the revenue. And this is defined over all the dairy products. So using the Gurobi Python API is so natural to do it. There is something called a quick sum function that you might think of this function as the sigma. So when you say quick sum, basically you are creating a summation. And in this particular case, we have the two variables, the quantity that we are going to demand it over each daily product, and the price of that daily product. And this will run over all the daily products. And then we have another method defined of the over the model object that we call model, that is the set objective. So in this particular case, this linear expression, we are going to call it object, and that's what we have here. I could do it differently. I could directly in the set objective method, I could define this thing, but just to be more clean, I define this parameter here, and then define the linear expression in terms of that parameter. The default in Gurobi is to minimize, so we need to tell Gurobi that we are maximizing. We have also another constraint that for each raw material or component, if we want to limit the production of dairy products to the capacity. So for that purpose, we need to generate the constraint. So we use the add constraints method, and the name of that method is going to be called fat capacity. Should be called component capacity because this is for the both components. But and then this method, we basically we just translate the inequality that we have here in terms of the quick sum. So quick sum is the summation of the product of the quantity pair of producing dairy product D and consuming raw material C times the volume or the production of dairy product D. And this will run over all the dairy products. So if you see, the summation here is very naturally expressed by this code here. And then we have the less or equal term here, and then the right hand side is the capacity of each component, and we have a for loop that will generate all the constraints for all the components, and the name of this constraint is going to be fat cap. We have another constraint that essentially establishes that the new prices must be such that the total cost of last year consumption would not be increased. So that means that the consumption times the price, which will represent the cost, should be less or equal than the price index that we have from the previous year. So again, very natural, we use the add constraint method, but in this case, we don't have the S here because we just have one constraint, and then we use the quick sum to express the left-hand side of the inequality. So this is a parameter, and this is a decision variable, and this is this summation is running over all the products, less or equal than the price index, and this this constraint is going to be called price index. And for the elasticities, we are going to approximate the elasticities with linear relationships, and I'm not going to discuss the details of these. These are just the formulas, and the Gurobi Python code here is just essentially copying the formula in terms of the add constraint method. And what I want to emphasize here is if you go to the H.P. Williams book, and these pages 334 to 335, you will see that H.P. Williams needs to do a lot of acrobatics to solve this problem. First, using the elasticity relationships, he expressed all the problem in terms of the prices. And then he used a transformation that makes the problem separable in terms of the price decision variables. It's going to be nonlinear, but separable. And it happens that this problem is convex, so he was using the conventional simplex method to solve it. But in general, these acrobatics that they use to be able to linearize the problem or to make it separable and all of that might not happen. The quadratic problem might not be convex and things like that. So what is happening now with Gurobi 9.0 and 9.1 is that you can solve these problems directly without any acrobatics, and this is very powerful because you just focus on making sure that your model represents reality, and then Gurobi will figure out how to solve it properly. You don't need to do too much math there to solve it. And this is the run from Gurobi to solve this quadratic problem. This is the optimal solution, and we have this gap. And basically, the optimal solution will generate 2.066 billion dollars, and this is the price, and this is the demand that you will have of milk at the given price. So this is the way that you will solve this quadratic problem for this agricultural pricing problem. So let me just, if you are interested and you want to play with this Jupyter notebook that we have created, in this presentation there is a link, so you can download this Jupyter notebook and play with it. You will need a license, but now we are developing a pip install for a limited license that should be able to solve this problem well. So you can use our pip install. So now let's talk about another problem. We call this problem the decentralization planning problem. And the statement of this problem is as follows. Given a set of departments of a company and potential cities where these departments can be located, we want to determine the best location of each department in order to maximize gross margin. And gross margin is defined as the reduced cost from relocation, and we are going to call this benefit, minus the increased cost of communication. And this is an example of a facility location problem that is formulated as a quadratic assignment problem. And we are going to use the Gurobi Python API, and we are going to solve it using the Gurobi optimizer. And this problem is example 10 from the H.P. William book. So just some comments here. Traditionally, this quadratic assignment problem, it can be linearized using a MIP formulation, and I'm not going to enter the details. I bet that most of you knows this formulation. Essentially, you need to add artificial auxiliary variables that we are going to call that you can call Y, for example, that express the product of binary variables. And in this particular model, these binary variables are the location. Where do you locate each department at which city? So this Y variable is going to be equal to 1 when the product of this variable is equal to 1. And then you can add constraints to really make sure that this logical constraint of if and only if happens. And these are classical constraints that you have to linearize quadratic problems. The problem with this linearization is that the combinatories can explode tremendously here. Because if you have many departments and many cities, then you will have a lot of thousands of these binary variables that may create this problem very difficult to solve. So being able to solve the quadratic assignment problem directly is really powerful because you don't need to have this linearization. So let's do that. Let's formulate this simple problem using the Gurobi Python API, and we are going to formulate it as a quadratic assignment problem. So this code basically will do the same thing. You always will need this type of code to use the Gurobi Python API. Will you bring you import the Gurobi Python module and other Python libraries that you want to use for your problem. And in this particular problem, the data are the departments. The departments are represented by a list, and this we are going to have 5 departments: A, B, C, D, and E. And we have another list to represent the cities: Bristol, Britain, and London. And we are going to use a multi-dig to represent the benefit. And the keys of this multi-dig dictionary is going to be a tuple. That the tuple will have the department and the city where that department can be located. And if department A is located at Bristol, the benefit is going to be $10,000. And the information is similar for the rest of the departments and cities. Essentially, D2C is the cross product of departments and cities. And to define the communication cost, we are going to define it for each possible combination of department city, which another department city. So in this particular case, the tuple A London, C Bristol means that the department A is located in London and department C is located in Bristol, and the communication cost between department A and C is going to be $13,000, and the rest is similar. The interpretation is similar. So that's the data of this model formulation. So let's build the optimization model given this data. So again, we will have a model object that we are going to call it model. We are not very creative. And this will be the name that if you print this formulation, you will see this name as decentralization problem. And basically this model object will contain all the objective function constraints and decision variables. So to solve this quadratic assignment problem, we need to invoke the global parameter non-convex, and we set that parameter equal to 2. So that's what we have here. And then to define the location variables that will say in which city each department is going to be located, we use the advars method, and the indices or keys of this object locate is going to be defined by the cross product between departments and cities. In this particular case, we are going, these variables are going to be binary. So this is not the default. So we need to tell Gurobi that these are binary variables, and this is the name of the variable. And the objective function, we use the set objective method. And again, we are going to use the quick sum to define the objective function. So the quick fun, this first term essentially define what will be the total benefit that we get from allocating a department at the particular city. And then we are going to subtract the summation of the communication cost from allocating department D at CTC and department D2 at CTC2. And this is multiplied by the location variables of locating department to a city. And this is going to run over the keys of the communication multi-dictionary. And we need to tell Gurobi that we are maximizing. We have a constraint here that a department must be located at one city. And we use the add constraint method, and we use the quick sum function, define it over the locate the variables. And so this summation here is going to run over all the cities. So for each department D, we are going to decide in which city this department D is going to be allocated, and the summation is going to be equal to 1. and then we have this for loop that is running over all the departments, and this is the name of these type of constraints. Also, we have another constraint that says that that no city may have more than 3 departments. So for each this type of constraints, for each city, we need to ensure that that city doesn't have more than 3 departments. So we use the add constraint method. We use the quick sum to represent the left-hand side of this constraint, and this should be less or equal than 3. So this is the beauty of the Gurobi Python API. You write your equation and it's very natural to translate your equation in terms of the Gurobi Python code. And you run this. This is a very small problem, so it runs in a fraction of a second, and you get the optimal solution without any gap. And this is the output. So you get the total benefit, you can compute the communication cost, and this is what you are optimizing, the gross margin, and this is the allocation. If you want to learn more about this particular example, you can go to our website and download it from our website. We have a Jupyter notebook there. Let's talk about another problem that is very interesting for many people, including me. This is a very important problem. This pooling problem is very important in continuous manufacturing, and it has many applications. For example, in the petrochemical refining, wastewater treatment, mining industries, supply chain operations, food and liquor processing. I like that one. Let's define the problem. So for a given list of source nodes with raw materials containing known attribute qualities, what is the most profitable way of mixing these materials at intermediate pools so as to meet the demand and tolerance at the multiple target nodes? And this type of problems can be represented by a tripartite graph. So this is a mixed integer quadratically constrained problem that we are going to formulate using the Gurobi Python API. So again, the first the code needs to import the Gurobi Python module and other Python libraries. And the particular instance that we are going to formulate using the Gurobi Python API is as follows. We are going to consider a tripartite graph that has 3 source nodes, S1, S2, and S3. And for each source node, like S2, we are going to have the availability of oil coming from this source node. So in this particular case, we have 6,129 barrels of oil available each day, and $62 is the cost of that oil. And then there are several attributes. These are chemical components in this type of oil, and this is the concentration of these numbers here are the concentration of those chemical components per barrel of oil. And then what we need to ensure at the end is when we start mixing this oil at the pool nodes and then at the target nodes, we want to ensure that the quality of the blended oil satisfies minimum and maximum tolerance level for each of these attributes that defines the quality of the oil. So for example, for DEN, the minimum is 0.74 and the maximum is 0.79. No? So that blended oil needs to be within these ranges, and similarly for other components. And this is the demand that at least we need to satisfy. We can produce more oil, and this is the price. We are going to sell it at this price. Also, we have capacity at the pool nodes. And this is the capacity at the pool 1, and this is the capacity at the pool 2. Also, there might be a pipeline between source nodes and target nodes, and this is the capacity of these pipelines going from source nodes to target nodes. And now we are going to use Python and the Gurobi Python API to represent this data. So the attributes of the oil is going to be defined as a dictionary. And we are going to use the multidic function to define the parameters of this model. So the first multidic function that we are going to define is over the source nodes. So, and for each source node, we are going to define cost, supply, and content based on the attributes of the oil, of that oil coming from source node. So the keys here are the source node, S1, just a single, it's a tuple, but it just has one element. And the price is this 49.2. This is the availability, 6,097.56. And this is the content. So the content of DEN is 0.82, benzene 3, etc. No? And we are going to have another multidic to define the parameters associated with the targets. So the price of oil blended at target 1, T1, is going to be $190. The least demand that we need to satisfy is going to be 500. And these are the minimum tolerance and the maximum tolerance that we need to have at this particular target node. And similarly for the other target nodes. For the capacity, to define the capacity of each pool, we have a multidic that has as keys the pools, and this is the capacity that we have at each of the pools. Then we are going to create data structures that will facilitate the creation of the decision variables. And for example, S2P will be the cross product of sources to pools. P2T is going to be the cross product of pools to target. And S2T are going to be these tuples that define flows from sources to targets. So here we don't have the cross product, so we define the tuples that will have flows associated with them. And let me explain the decision variables. We are going to use a formulation that is called the Q formulation, and we use a paper by Gupte, Ahmed, Day, and Chion. And this is a great paper with several formulations. And this formulation is very efficient, creates a tight formulation that Gurobi can solve very, very quickly. So the decision variables in this Q formulation is going to be flow, and this will be the flow from node I to node J. And so we are going to have flows from source nodes to target nodes and from source node to pool nodes. No, to pool nodes, no, we don't have flows. Sorry, that's a mistake. We have another variable for that. So flows from source nodes to target nodes and from pool nodes to target nodes. And we are going to have another decision variable that is a fraction of total inflow at pool node P coming from sources S. So this proportion of flow going from source node S2 to P1 is going to be represented by this prop decision variable, and these variables are going to be continuous. So we are going to build the object that will capture all the elements of the math programming problem here. And in this particular case, we were more creative, and we call it Q pooling. So this is the object that will capture all the components of a math programming problem. And again, this is a bilinear model that we are going to set the global parameter node converse equal to 2, and we set a limit of 30 seconds. And we are going to define the different types of flow variables. So flow ST Basically, we use the adverse constraint from source nodes to target nodes, and not all of them has, so that's why we created that dictionary that I defined before. And then we define P2, and these are the cross products of pull nodes to target nodes. So we will have flow variables defined by those indices. And then for these particular flows from source S to target T, from S1 to target T2, we have an upper bound of 750 barrels, and similarly for this other flow. And the add variance method is going to be defined for the source nodes and pull nodes. So we use the add variance method here, and the upper bound is 1. And the name of this variable is going to be prop source to pull. So I'm going to skip this explanation because I don't have much time. So I'm going to go directly to the code, and you can read the paper to really go into the details about the formulation. So in this particular case, we want to define the capacity constraint at each source node. So again, we are going to use the add constraint variable. So this first term really represent the flow going from leaving the source node S and going to different pull nodes. So it's all the outflow leaving the source node S. And this term here is all the outflow of source node S going to target nodes. And the constraint essentially is to copying these inequalities using the quick sum. So this first quick sum really is exactly as this term that we have here, and then this term here is represented by this. In this particular case, we don't use the quick sum. We use a method called sum defined over the flow ST variables, and this should be less than equal the available supply at each of the source nodes. We are going to have a constraint for the pool capacity, and again we use the add constraint method. Again, we didn't use how it's called the oh, I forgot the name, the quick sum method. We use directly the sum method defining of the variables flow PT. So this term here really represents the summation less than equal the capacity. And then you have a for loop to define capacity constraints for each of the pools. And then for the target nodes, basically we want to ensure that the flow going to that particular node, at least you will produce at least this amount of oil, blended oil. So the first term, the first term basically represents the inflow of oil coming from source nodes at the target node T. And this second term represents the inflow at target node T coming from pull nodes P. And then the representation using the Gurobi Python API is just basically copying those equations in terms of the methods that I just described. So there is no much to explain here. We have another constraint that ensures that the proportion variables for each pool. So all the proportion should be equal to 1. So for each pool node P, we want to ensure that all the proportion variables going to that node, the summation is equal to 1. And the constraint is the way that we represent it in Gurobi is very similar. It's just copying this thing. This is a more complicated constraint. Again, I don't have time to explain all the details, but the key idea to express the mean target tolerance constraints is that you consider the weighted average of the uh, concentration of the attributes of the blended oil at each target node. So you want to satisfy this minimum tolerance at target node T with the oil blended oil attribute K. So this first term here really represent is based on the content of attribute K from source node S. And this first term here represent the concentration of that attribute K from all the source node S. And here you are going to represent the concentration of attribute K coming from the blended oil from all the pool nodes that are sending oil to the target node T. And again, the way that you represent it in Gurobi is just to copy this inequality. And we have a maximum target constraint. So the left-hand side is exactly the same. And the difference is that in the right-hand side, you will have maximum tolerance and the inequality is going to be, so the maximum tolerance should be greater than the average, the weighted average of concentration of attribute K from pool nodes and source nodes. The objective function, here the objective function is to maximize profit. So the first term here represents the revenue generated from all the target nodes. And the second term here is going to represent the cost. So basically the cost of oil coming from each of the source nodes. And again, I don't have time to go into the details of this equation, but to represent it in Gurobi, basically you just quiz sums for this, and you can see that the equation exactly maps what I have explained, or I briefly explained here. And to represent the objective function, we use the set objective method defined over this expression object. This is the output from Gurobi, and for this particular formulation, it runs in a fraction of a second. The gap is 0. And the model is relatively small, but if you use another formulation, you will see that the convergence is much more slower. And this is the maximal profit that you can get. And this particular problem, you can represent it very nicely with some graphic interfaces. So in this particular case, the flows, the optimal flows are represented with red arrows or red numbers. So the optimal flow from S1 to P1 is 325 barrels of oil. And here is the production, the blended oil that you are going to have at each target node. So you see that we are producing, mostly we are producing more oil than required, except in this target node. And in this side, you see that the optimal solution satisfies the minimum and maximum tolerance. And also, there are other interesting KPIs that you can build here. So, for example, these are financial KPIs. So you can compute the total cost of blending this oil. And you have it here, and you can also compute what will be the cost of at each of the source nodes. And similarly, you can compute the overall profit from all the target nodes, which is this number here, the overall revenue and the ROI. ROI is defined as revenue divided by cost. But also you can define profit, revenue, cost, and ROI at each of the targets. This is a little bit more complicated to compute it, but you can do it. And as you see, target node one is very profitable. It's about 75% of the profit comes from this target node. And there is other KPIs that you can produce here that I'm calling operational KPIs. And so you can compute the capacity utilization at the source node, which is 17.6%, and the utilization of each of the source nodes. So you see that this source node is fully utilized. So there might be advantages of buying more oil from these. Also, the capacity utilization from the pools here, and the overall demand fulfillment. So if you see for target node one, you are producing 5 times the required demand. So this is because this pool node is very profitable. So sorry that I had to go so quickly. We didn't have time for more details. You can download this Jupyter notebook from our website, this link. And if you are interested in the theory, our R&D director, I think now he's VP, Toby Arkedberg, he has a very nice presentation about non-convex quadratic optimization. So I strongly recommend it if you want to see the theory behind this. And I will stop here, Bill. So
thanks, Pano. That was great. It's a lot of information, and accordingly, we have a lot in the Q&A. We'll get to as much as we can.
Okay.
And then anything else that we have, obviously we have a log of this, and we can respond to the questions so that everyone can see them in a follow-up. But let's kick it off real quick. And we'll start from the top. And David, who had sent a question in the early part of your presentation with regard to agriculture. In the agricultural example, the price index is assumed not to go up from year to year. In view of inflation, don't prices need to increase from year to year? Is his question that he has posed.
Yes, and you are thinking exactly as a practitioner. Basically, the intention we were using the example for H.P. Williams, so we use the model as he presented in the book. And when I saw some of the formulations, I also start thinking of some extension and all of that. But you are exactly thinking as a math programmer practitioner, where you say, oh, okay, this formulation is too limited. And yes, needs to consider inflation. So that's a great observation to improve the model. So try it. Go to our website, download the model, and start playing with it.
Great, thank you. Antonio has a question. What to do when you can't reach an incumbent in your problem in a feasible time?
In general, for any problem, this is a very good question, because many times to solve these non-convex problems, that's the issue, no? That how to find an initial feasible solution, and we have a certain functionality now that allows to find a feasible solution quickly for this type of models. At this point, I don't remember exactly how to do it, but send us that question and we will find out from our support or R&D team how you can speed up and find the an initial feasible solution. But that's a great question, because many times for these non-convex problems, that's the first thing, find an initial feasible solution. Thank you.
Great. Next question is from Jen Chun. Price index is a input value at the beginning. Later, when using it to create the constraint, price index is assigned to the corresponding constraint. Is it right? Is that right?
Yes. Yes, the price index is a constant. It's a given. So you want to ensure that the prices that you set now satisfy, which will represent the cost. So the cost of consumption will satisfy the price index of the last year.
Great.
Yes,
Thank
you
you.
are.
Krishna has a question for the agricultural problem. Is the final solution reported by Gurobi global optimal?
Yes, yes. But this is a very good question.
We got a lot of those.
Yeah. Well, all of them are good, but you, solving these non-linear problems, then depending on the machine that you have, you might get different precision on the gap. And yes, always that's the beauty of Gurobi. We guarantee global optimality all the time, and then that's why we report the gap. But depending on the version of the of the solver and that you have, and the machine that you have, that gap might change. So if you download our agricultural problem, depending on your equipment, you might get different numbers. But the number that you are getting is optimal, and it satisfies our tolerance of optimality conditions.
Great. Another one comes from Anton. Will the separable reformulation run faster than the non-convex version of the problem in Gurobi?
I don't know. I haven't tried it. I go to the book, download our Gurobi Python API and try it. But as a practitioner, that approximation, it has a lot of things in the approximation, so you will lose precision there. If you solve it directly, you won't have that problems of precision. But that's a great problem to solve. I might create an exercise there for people to try the formulation that the HP William has, and compare it with what we have. Thank you. Good.
Great. Apostolos has a question. How do you set an optimal gap of example 1% and a time limit, example 1 minute also? So if either of the two limits is reached, then the Gurobi would give the best estimate so far. Is that?
Yeah. At this point, I don't remember the exact instructions that you need to give. So exactly, basically, what you are trying to do is to have a gap limit and a time limit. So at this point, we have a time limit. So I will let you know how do you set the gap limit. So
Okay.
when you reach either of them, then the model will stop and give you the solution for that particular time or gap that you have defined. I don't remember it, but yeah,
Okay.
that's in our documentation.
Nicholas has a question. Is it beneficial numerically to introduce binaries into a pure bilinear continuous problem? Quantity times quality. You're gonna have to read this one. I think we'll have to get that one. There's a little bit of formulaic stuff in there. I want to make sure that we answer correctly. So we'll with that. That's one promise that maybe we can answer offline. Anything
Yeah.
with some of the high math. Do you see the question?
No, I don't see it.
Okay, well, we can get to that one. I'll get one with a little bit. Is the decentralization optimization suitable to find optimal locations for electrical vehicles charging stations? is the decentralization optimization suitable to find optimal locations for electric vehicle charging stations, is the question.
You need to give me more information. Yeah, I think you have a problem in mind. It can be very interesting. I will love to learn more about
Okay.
your problem, but at this point, I don't have enough information
Right.
to really answer that.
Okay. See if we can get a couple of more in here. What's the difference between using quick sum than dot sum in the constraint?
Good. As I understand it, quick sum is faster. So I think Greg Glockner recommend quick sum. Sometimes you use the sum method because it's easy to write. Overall, in these problems that are not that big. I think there is a difference in efficiency between quick sum and the sum method. And I think Greg recommends the quick sum. But this was just the modeler for quick of developing the code, use both in some cases.
Yeah, no, there were about 3 or 4 questions about this of that same question, so we knocked out a few of them on that one. And let's last one that goes back to the agricultural problem. What is the computational effort of the agricultural problem using Gurobi? Does that?
I don't know. What do you mean by computational effort?
Okay, well, we can. That's another one we might be able to get back to. There are several more, and I think maybe what we can do is we'll pull this out and try and answer these offline. Does that sound good, Pana?
That's fantastic, and thank you for the question because that will enrich this presentation.
Yes, I completely agree. Thank you, everyone, for all of your questions and continuing to send questions as Pana was answering questions. I think we have a lot of good things in here, and we appreciate both your time and your engagement and joining us today. So thank you all. On behalf of Pano and Isela of Gurobi and me from Informs and the rest of the Informs team, thank you for joining us today. We will have a recording of the webinar available on our YouTube channel very soon. And we encourage you to visit Gurobi's website. And as Pano said, we will also be sending out the presentation where you have, as you can see, lots of resources and links that you can follow. And as Pano said, you can go in and play with some of this on your own, right? Some of the things that you've provided, there's a nice little playground to go and do some of these things, and maybe even answer some of these questions on your own of the things you've seen and done. So, yeah. Pano, anything else to add?
Oh no, love that you try these examples, and thank you for being here. And big hug to everybody.
That's right. Thanks, everyone. Have a wonderful rest of your day wherever you are, and we'll talk to you soon.
Bye.
Bye-bye.